here's the problem. It's from 2017 Silver, and it's called Why Did the Cow Cross the Road? Okay, so the problem statement is we have a bunch of cows that are trying to cross a road, and each of them wants to have like a chicken to guide them across the road. So we know that chickens, there's C of them less than or equal to 20,000, and every chicken can only help a cow at one point in time, which is TI. And then for the cows, there's N of them, and N is less than or equal to 20,000 as well. But they have this range of times from A to B for each cow that they can cross the road at, and then a cow and a chicken can be compatible and cross the road together if the chicken's time is in the range of the cow's time. Okay, so we're asked to find the maximum number of pairs that we can make so that like the cows can cross the road successfully with a chicken as their expert guide. Yeah, and then there's some sample input stuff, which we'll look at later. But that's basically the problem. So yeah, the idea of this is that we're trying to maximize this value. And in order to do that, we're going to use something called a greedy algorithm. So it's basically what it sounds like, where the objective is to take as many pairs as possible. And so each step that we take in this algorithm is going to be actively working towards that goal of taking as many pairs as possible. So yeah, to give a relatively simple example of this, that's actually pretty similar to the problem itself, is this problem called the scheduling problem. And yeah, it's like a basic example of greedy with some nuances that you can like work out. And you can find this on Usico Guide for Silver. Yeah. So basically the problem is we have n events. You probably have noticed that they use n for pretty much all of the problems to signify some variable. But yeah, we have n events, and each of them have a start and end time. And then basically we can go to some subset of these events as long as we are like going to the full event for the whole duration, and we can't be at two events at the same time. And also we can like go between different events with basically no time. And the question is to find the maximum number of events we can go to. So yeah, you can probably see the parallels between these two problems, in that like we have these kind of events which would be crossing the road in the Usico problem, and then we're trying to find the maximum number of these events, which would be like a pairing to cross. And of course, we're maximizing it. So yeah, the first thing that might come to mind to find out how to do this problem is we could repeatedly take the next event that starts the earliest. So for example, if we have like this, and what we're going to do is the first event is obviously the first event that we can go to, so we can just take it. And now it ends right here, which means that the next event that we can go to, because this one is out of the question, because it's already started, the next event that we can go to and the one that starts the earliest is this one. So for example, if there was like something like this here, we would take this event instead of this one because this starts earlier. So yeah. This would give us 2 events total. And for this, for this case, the answer turns out to be right. We can't get any more than 2 events. But the problem is that there are some, or like many counterexamples to this algorithm that prove that it doesn't work. So one of these we can look at is if we have this really long event that starts the earliest and some other smaller ones that start later, but they don't overlap each other. So according to this first algorithm, if we apply it here, we would get just take the one that starts the earliest, go to it, and now there's nothing here after this first event's endpoint. We don't have anything. There's no more events, which means the answer that this would give us is 1. And you can probably see now that like 1 is not the answer. We can do better than that. And the way we do this is by taking these 3. So yeah, the reason that the first example or the first algorithm didn't work is because we're just taking the one that starts the earliest regardless of when it ends. And so in this case, it starts really early, the first event, this one, starts really early, but it ends really late, which means when it ends, we have no more choices. Or if there was like stuff after it, we would have less choices than we would if we took an event that maybe started later but ended earlier. So yeah, by doing that, we can form another algorithm, which is just to take the next earliest ending event. Yeah, so you can see that these 3 follow this algorithm. And you can prove that this is optimal and that like by being greedy using this algorithm, we can always get the correct answer, either by kind of reasoning it out by saying like if it ends earlier, then that means we have a bunch more flexibility to do whatever we want afterwards. Or you can also take like 2 events, event 1 and event 2, and compare like how taking those would affect the total number of events we can go to. So yeah, the idea of this is that you have to kind of think through when an algorithm that is greedy is actually going to work and like gives you the correct answer. So for this first one, it actually doesn't work, right? So it's not correct. And another example of this is if we were to do a knapsack problem. I'm not really sure if this was covered in the DP talk, but like we have a bunch of items with weights and values, and we can only get a limited number of, or a limited weight total, and we want to maximize the values. So if we were to try to formulate a greedy algorithm that works for this scenario, we're trying to maximize the total value. So if we just take like all of the items that like have the biggest values, they might also have really big weights and not leave enough room for any other items, which would be a problem. So yeah, in this case, we would use DP. And this is like an example of not every action has to be aligned with your goal in order for us to maximize the total value. So that was kind of an aside, but yeah. The reason this helps us is because we can actually see that this problem, the scheduling one, is pretty similar in that we're looking at these chickens and we have these cows. So for each chicken, if we sort them first based on their time, we have 2, 6, 7, 8, and 9. So if we just go through the chickens and see like if we can pair a cow with it, then for 2, it falls into 2, 5, and 0, 3. And using the principle that we discovered before, we're going to take 0, 3 instead of 2, 5. It's not because it starts earlier, but because it ends earlier, because 3 is less than 5. And then we do the same thing for 6. So we have 0, 3 is crossed out. 6 only goes into 4, 9. And then 7 only goes into 8, 13. And then 8 and 9 don't fall into any intervals. Which means that we're not really going to do anything with those chickens. Yeah, so this problem, the samples weren't like super instructive, but the basic idea of it is kind of summarized in the scheduling problem. So yeah, this would give us 1, 2, 3 as our answer. That was it. Thank you.